All right, this is going to be the video for differential equations, section 8.1, which is the first of the sections of systems of differential equations. So this first one, we're not going to learn methods to solve yet. We're going to do that kind of introductory section where we have to talk about terminology and notation and just the ideas, and then we'll kind of get into the actual solution methods in later sections. All right, so first, for a system of differential equations, actually for a system of just regular equations, the solution is the values of the variables that make all the equations in the system true, right? For a system of differential equations, then the solution is the set of solution function curves for each of the dependent variables that make all the differential equations in the system true. So finding a solution set, it means to find a set of general solutions or specific solutions that solve the system. In the first section here, we're going to learn terminology notation, and a lot of these ideas are going to be similar to things that we've encountered for single differential equations, but we're going to have much stronger emphasis on matrix. So we're going to use matrices a lot here, and I'll review a little bit of stuff about matrix arithmetic and how that works. But if we encounter something here that you're not familiar with, you can come and see me in tutoring, and I can go over a better review of just matrix methods by themselves. All right, so let's consider a system of two differential equations. Each is going to have a different dependent variable, but they'll both have the same independent variable. So typically in this section, we're going to use t for the independent variable, right? Like the x variable. But that means that we'll have one differential equation, which is the variable x with respect to t, and then the other one is going to be y with respect to t. So they're both differential equations where t is the independent variable, but then they have two different dependent variables, x and y. Right? So typically a system of differential equations will look like this. You'll have one row, which is a differential equation where we've got the first order differential equation, dx dt equals some function. And then we have a second row, which is dy dt equals a function, right? And what can be on the right-hand side can be mixtures of x and y variables for both equations. Plus, we can also have a part which is dependent on the independent variable. It can be constants or it can be functions of t. Okay, so we're going to deal with the part that has got the variables separate from the part that is just the portions with constants and t's. This portion out here kind of corresponds to the right-hand side for a differential equation, and this part over here corresponds to the corresponding homogeneous differential equation. So just like before, we're going to find that the general solution consists of a complementary solution to the corresponding homogeneous system plus a particular solution that solves the system with the right-hand side not equal to 0. Okay, so for this particular system, if we eliminate this portion here and just keep this part that has the x's and y's, this right here is the corresponding homogeneous system of differential equations. And we'll solve that first, typically, and then we'll use other methods to get the particular solution. So just like with the single differential equations with systems, we have a homogeneous part and a non-homogeneous part. Okay, let's say, for example, that this system of this homogeneous system happens to have this particular solution. We will call that solution the complementary solution. Since we have a differential equation dx dt, it means we have one solution which is a function of x. X is a function of t. So x as a function of the independent variable t is equal to that. And then we separately have dy dt here, so we have y as a function of t. And that means that we have a system of solution curves as this complementary solution. And in the general case, we have undefined constants for C1 and C2. The C1 and C2 constants are the same for both of the rows. And that's why this is so nice to be able to do with matrix methods, and we'll see how that works. Okay, if we were given, let's say, we don't know yet a method for solving for these complementary solutions, but let's say we were given that this we thought might be a solution for this system, we could verify that by taking each of the equations, x and y, and taking its derivative with respect to the independent variable t. And then we can plug the x and the y and the dx dt and the dy dt into the system in the various places that they appear, and then verify that all of the differential equations are true, right? So if we work with this top equation first, right, here's in the notes it shows that if you plug in this for dx dt on the left-hand side, and then you plug in this for x and this for y, those two sides are in fact equal, and you verify that the solution set is a fundamental solution for the first line of the system, and then this is the step showing it being plugged into the second differential equation. So you plug in the dy dt on the left, and then you plug that same x and y in on the right. Okay, so you could verify a given solution is a solution to the system by taking the appropriate derivatives and plugging them in. Okay, when we include the part out here, which is not containing the x and y variables, the non-homogeneous part, then we get what's called the particular solution, which is also labeled xp and yp. It would typically be functions that could contain a t, the independent variable, and the same thing, we could take the derivative of each of those and then plug the x and the y and the dx dt and the dy dt into the system to verify that the particular solution for x and y makes all the differential equations true in the system. Okay? So the notes are posted if you want to look through that in more detail. Just want to verify, just know that you can verify a given solution. Okay, but the more important thing is we're going to do lots of things with matrices here. So we're going to take a system that's written out line by line and convert it into what's called matrix form or vector form. So I'm going to use the term matrix and vector interchangeably because they're related and they're kind of basically the same thing. What we're going to say is that if I have dx dt and dy dt, that means I'm taking the derivative with respect to t of x and y. So I'm going to take the x as the first row and the y as the second row, and I'm going to make a matrix, or you can call it a vector, called capital X, and I'm going to use the arrow notation for vectors. This also same thing for matrices. In the textbook, they used to use bold letters, but this X matrix, if I were to write it out here, is a 2-by-1 matrix that has the variable x as its first row and the variable y as its second row. And so that means that this dx dt dy dt can be collapsed into one object, which is a matrix that's d dt of x and y. Okay, and then we're going to say if I've defined x as the matrix xy, then that means I could write x matrix prime as containing x prime y prime. So this expression here typically gets replaced with the symbol x prime, matrix x prime. Okay, so then how do I deal with the right-hand side? So I'm going to use a different color here for that. Well, first of all, I can take the same x variable here, or the same x matrix, and just pull off the constants, 1, 3, 5, and 8, and make another matrix here of those coefficients, 1, 3, 5, and 8, because when you do matrix multiplication, let me show that over here. If I have 1, 3, 5, 8, or 5, 3, multiplied by the matrix xy, then that means that first we're going to produce, this is a 2-by-2 matrix, and this is a 2-by-1 matrix, which means that since these match, we can do the multiplication. We're going to get a resulting matrix which has 2 rows and 1 column. And so when I work on this first thing, I'm going to take this value times this value, which is x, and then I'm going to add this value times this value, which is 3y. And you see how that recreates x plus 3y? So this matrix multiplication is defined this way specifically so that you can write a system in matrix form. We could also say this element down here, the second element is 5 times x, right? We take this column times, or this row, the second row on the first matrix times the first column, and then so that'd be 5x plus 3 times y, and that recreates the 5x plus 3y. So this structure here replicates this structure here. Okay? And then what do we do about this stuff out here? Let me use a different color. Pick orange. Okay. What do we do about this stuff out here? Well, we just tack another matrix on there that has plus 12t minus 11 as its top element, and as the second row element, it's negative 3. Right? So typically, this is now all collapsed using symbols. So we take this part here and we replace it with the symbol x prime. Right? We take this here and just use the symbol x. And then a lot of times we take this whole matrix and give it some name like f. And and then we just have a coefficient matrix here that when we multiply it out, it recreates everything. In fact, sometimes this matrix here, we'll split it because I notice I have some terms that have a t in them and some that just have constants in them. So you could consider this to be 0t minus 3, and then you can write this as the matrix 12, 0 times t plus another matrix with just the constants, negative 11 and 3. So this is actually the most common way to write this system as, let me erase this and show that this is the same as this, right? But written out in matrix form. So we have a matrix x prime to represent the derivatives on the left-hand side. We have a coefficient matrix times the matrix x. And then we have the right-hand side with a column for t and a column for the constants. All right? So we're going to be dealing with systems written in matrix form. So one of the things we're going to cover in the homework tonight is just being able to convert back and forth between the separate equations in the system and the matrix form, and then vice versa. All right, a couple more things to know. So that means that since the system itself can be written in matrix form, the complementary and the particular solutions can also be written in matrix form. So if I have a solution that looks like this, then because it has the same constants here, C1 is the constant for the first term in both of them, and because this part is the same, that means that you could make that into a matrix where the first row represents everything here and the second row represents everything here. So what I've got is I've got C1 times 1 times e to the negative t plus C2 times e to the negative t, right? So you can see how this works back out. If I wanted to kind of write this back out again, you could say, all right, I've got this matrix. Let me use a different color. So this matrix here is xy. Right? We have a C here that's going to be multiplied everything over here. And we've got this matrix 1, negative 1. And then this is copied for both of these, if you wanted to think of it like that. And then we've got this C2 that applies to all the rows, 3, 5. And we've got this e to the 6t that applies to all the rows. And so you can see how this is really saying that x equals C1 times 1 times e to the negative 2t plus C2 times 3 times e to the negative 6t, and it replicates this row, right? And then the second row replicates the y row. Okay, the same thing is true for the particular solution. So if we have a particular solution, we have a solution for x and a solution for y. We can just say x for the particular solution is the first row, 3t minus 4, is the x particular solution, and the minus 5t plus 6 is the y particular solution. So everything in the first row always relates to x, and the second row relates to y. Okay, so those are matrix forms. Now, we know from single differential equations that the general solution is comprised of the homogeneous corresponding solution, C, plus the particular solution, P. And the same thing is true here, except we would just say that the total solution matrix is equal to the matrix for the complementary solution plus the matrix for the particular solution. Right? So we could have something like that, right? And that means that if you were to recreate all this, right, you're going to have the portion, since all the rows add together, you're going to have the portion from XC added to the portion from XP, and the same thing in the second row here. All right. All right, so we can go back and forth between separate equation form and matrix form, whether we're talking about the system or whether we're talking about the solutions of the system. All right, now let's talk about how do we graph the solution, because the solutions are functions, so they can be graphed as function curves, right? If we have a single differential equation, then typically we have y as a function of x, and we graph that on the xy plane, right, to get the solution curve. We have a whole family of curves, and then if we're given an initial condition, like one particular point, we pick one particular one for the solution curve, right? But in this case, we have three things, right? We have two dependent variables, y and x, but then we have one independent variable, t. So there's different ways we could graph, right? We could graph x versus t, y versus t, or x versus y. They all are used in different places. Let's say, for example, that the way we would figure out what these constants are is we would have to be given initial conditions, like when x is 0, x is something when t is 0, and then also when t is 0, y is something, or some other point. And you could use that to solve for the constants. So let's say that initial conditions were given such that C1 was 2 and C2 was 3. That means you can just plug that in here and here to get this is the general solution here. And this would be the specific solution curve that goes through the initial conditions point. Right? We have one row here related to the x and one row here related to the y. All right. So there's different ways you could plot. Now, the way we typically don't do it, although you could do it, is we could plot x versus t and separately y versus t. In other words, plot one of the dependent variables against the independent variable. And if you did that, you could take this and recreate the equation, right? Like this x equation is 2 times 1 times e to the negative t plus 3 times 3 times e to the 6t plus 3t minus 4, right? And then this one over here, yt, I think I actually have a typo in here. There's a 2 here because it's 2 times negative 1 times e to the negative t plus 3 times 5 times e to the negative 6 plus negative 5t plus 6. And you could graph x versus t or y versus t. That typically isn't done, though, when we consider things, although we could. I mean, you could look at how x versus t varies or y versus t. More commonly, we do what's called a phase diagram. So we've seen phase portraits before, or phase diagrams in 1D. Now we're going to have 2D phase diagrams, okay? And that would be if we plot x versus y, right? So we're going to make a plot that has y here versus x. And what that means is if you were to write out the equation for x, t, and yt, we have x versus t and y versus t, which means that this, you can consider that matrix X, the solution matrix, to be a position vector that goes from the origin to an XY coordinate. And the XY coordinates are given in terms of these two equations, which use t as a parameter. So thinking back to Calc 3, we're able to graph x and y versus the t parameter, right? So this is basically a set of parametric equations. And that means that we could, for example, plug 0 in for t and find that the point is here, x, y, like compute this value and this value, and then we get some point here, like maybe it's 7, like maybe this becomes the matrix 7 for x, and then 19 for y, or something like that, when you plug in 0 for t. And you plug plot that point, and then maybe we plug in a different value, like -1 in for t here and here, and we get a different matrix, like maybe it's going to be 7.8 for x, and it's -3.8 for y. And then we plot that point here, and if you did that for lots of parameter t's, you would trace out this curve here. Okay, now typically, this is called, you should probably cross this out. Typically, we don't call this a solution curve. We call this a trajectory. Solution curve is usually reserved for plots that plot the dependent variable versus the independent variable. So these are solution curves. But typically, we would call this a trajectory. And we call this XY plane the phase plane. And this whole thing is referred to as a phase diagram, a 2D phase diagram. It shows how, as you change the independent variable, both x and y change together in some linked way. And this would be with the constants established for some particular point. Right? If you wanted to talk about an entire phase diagram, it would be going back and resolving for these constants for different initial conditions, and you might have another trajectory on here that goes through some different initial condition. And if you do all of them together, it creates what's called the phase diagram. Okay. All right, so typically we plot the two dependent variables against each other in a phase diagram, or on a phase plane. All right. So for us to be able to claim that the different terms added together in the general solution for the homogeneous solution is a fundamental solution set, we have to know that they're all linearly independent from each other. So technically, that means that if you've got different solutions here, like x1, x2, all the way up to however many things you have, and then you have different components for the x, the y, and the z variable versus time, then you could use a Wronskian to determine, if as long as the Wronskian is non-zero, that the set, all the functions are linearly independent, and therefore they form a fundamental solution set. The structure for the Wronskian is a little bit different, though. So here's what it looks like generically. This is kind of the equation from the book, but it's easiest to see this with an example. So let's look at the example that we've been looking at here. Here's a complementary solution for the homogeneous set. Now, we don't know these constants, so we ignore those constants. But what we're going to do is just take the structure, so e to the negative 2t, the 3 e to the 6t here, the negative 1 e to the negative 2t, and the 5 e to the 6t here, and then form a determinant with everything just in matrix form, like just drop the unknown constants and copy the matrix. That is the Wronskian for the system. And then we compute it the way we would compute any Wronskian by just doing the determinant. So we take, this times this minus the other diagonal, and we end up getting 8 e to the 4t, which for all positive t's, well, actually for all t's, this would be a positive number. So this is non-zero, and that means that these terms here for both the x and the y are linearly independent of each other, and therefore together they form a linearly independent set of solutions for the system, which means that when we linearly combine them with these plus signs, we get the true general solution for the system. Okay, we're not going to do a lot with the Wronskians. We might come up here and there because mostly we'll just know that when we do these procedures, we get linearly independent. Because the methods we're going to learn, we can show with the Wronskian, if we wanted to, always produce linearly independent solutions first. Okay? Right, and the last thing I wanted to mention is that all this doesn't have to be restricted to just two differential equations. We can have any number of differential equations, each with its own dependent variable. We still have to have only one independent variable, so everything is with respect to t. The reason for that is if we had like an s and a t, then that means all the derivatives would be partial derivatives, and that's a much more advanced topic. Partial differential equations is a more advanced course. So we always have one independent variable, t, but we can have any number of dependent variables, x, y, and z, x, y, z, w, anything. So here's one that has three differential equations, dx dt, dy dt, dz dt, and that means that we generally can have x's, y's, and z's along with the non-homogeneous part in terms of t. And so the corresponding matrix here would be x prime. Well, x would now represent, it would be a 3x1 matrix because we have three rows, because we have three variables, x, y, and z, right? And x prime would be the derivatives of those. And then we would have a 3x3 matrix for our coefficient matrix with 6, 1, 1, 3, 7, negative 1, and so on. And then we would have three rows in the F matrix for the non-homogeneous part. Okay, now if you were to solve that and get the solutions, you would have x versus t, y versus t, and z versus t, which means you could consider this to be a position vector. It's like a position vector r, right, where you plug in t and you get you get an x, a y, and a z out. So that means you're plotting something through 3D space. Right, and that means that phase diagrams would now we wouldn't be calling this a phase plane anymore. We would call this a phase space if this was 3D. And the trajectory, which we should use the word trajectory instead of solution curve, this is a phase diagram. The trajectory would now be a path, a parameterized path through 3D space. And of course, once you go above 3D, you can't draw it anymore. But you could have a 4-dimensional space or a 5-dimensional space if you have 5 variables. Same with Calc 3. All that stuff is extendable to higher number of dimensions. All right, so that's enough, should be enough to do the homework for section 8.1. Give that a try, and then we'll have other videos for the other sections.